Um, and now we'll have the final talk of the day by Alessandro Lovato on solving the nuclear many-body problem with neural quantum states. And Alessandro, take it away.
Thank you for the introduction and for the invitation. I think the pointer is not working. All right, so let's start this journey. After the previous talk, it's going to be a little bit hard to convince you that nuclear physics is still interesting after decades after its inception. But I believe it still is, and neural networks can give us.
Is the microphone on? Quieter than one.
That's right, better. Thank you. All right, so let's assume that not everybody is familiar with nuclear physics, so I will give you a refresh. Everybody is familiar though with the planetary picture of an atom, where electrons orbit around a nucleus, which sit at the center of the atom. And the fact is that most of the atom is in fact empty. But on the other hand, almost 100% of the mass of an atom it's in the nucleus. So it's in this tiny object in the center. And in fact, the nucleus is much smaller than what I'm representing here. And in his famous experiment, more than 100 years ago, Rutherford said that if an atom were expanded to the size of a cathedral, then the nucleus will be the size of a fly. So that tells you how big the atom is compared to this tiny nucleus at the center. And nuclear physics studies precisely what happens at that center. And a nucleus is a self-bound quantum mechanical system made of protons and neutrons that is bound because of the strong force. So it's underlying theory of QCD, or quantum chromodynamics, that is responsible for the binding of the nucleus. But there is also a Coulomb repulsion because protons are positively charged, so they repel each other. And this is why if we look across the nuclear chart, on the x-axis, I'm showing the number of neutrons, on the y-axis, the number of protons. The strong force would like the nucleus to have the same number of protons and neutrons, but because of the electromagnetic repulsions, if you have too many protons, then the energy is increased, and the nucleus is not anymore bound. So the valley of stability, this black line, is actually underneath the symmetric case. So for stable nuclei, there are fewer protons than neutrons in general. And there are open questions in nuclear physics. Some are addressed by the FRIB, the Facility for Rare Isotope Beams, that was just completed at MSU. Some of them are, for example, what is the limit of stability of nuclei? How many neutrons can we add until the nucleus becomes unstable? Or where are heavy elements formed, like gold? It is believed, in fact, that gold is formed in coalescing neutron stars in the space. And these questions, in order to be addressed, they're important, they're interesting in their own right, but in addition, nuclei are also laboratory in a sense. They're used to investigate properties of the most elusive particles in the universe, which are neutrinos. Basically, to understand, for example, the matter-antimatter asymmetry in the universe, what neutrino physicists do, they create a beam of neutrinos, and then these neutrinos travel hundreds of miles underneath the Earth, and then they interact with a detector, which is made of nuclei, argon nuclei, specifically for the deep underground neutrino solution experiments it's under construction. And in order to understand the properties of this oscillated flux, we need to properly understand how neutrinos interact with nuclei. And this is, again, nuclear interactions play a key role in this regard. Another aspect is neutrino double beta decay. If we want to understand whether the very nature of neutrinos, so if neutrinos are their own antiparticle, we can observe this decay, which is forbidden in the standard model. And the rate of this decay is dictated by the nuclear matrix element. So the probability for a nucleus to transition from a given state to another. And again, it's strongly influenced by nuclear dynamics. So having a nuclear dynamics under control is critical for the design of these experiments and for interpreting a potential observation. And finally, there is also a nice connection with nuclear astrophysics. Believe it or not, but we can observe gravitational waves from outer space, and in particular, we can observe the gravitational wave signal on Earth, which is originated by coalescing neutron stars. So if two neutron stars are orbiting around each other, they spiral and then they infall. And the amount of material that falls from one star to the other is determined by the equation of state of the matter. So basically, how strong this matter is self-bound. And by looking at the gravitational wave signal on Earth, one can infer properties of nuclear interactions at extremely high densities. Okay, so in the energy regime relevant for quantum nuclear many-body theory, quarks and gluons are assumed to be confined inside protons and neutrons and pions. And the interactions is basically, instead of solving QCD, which is in this regime is non-perturbative and it's incredibly hard, we solve a quantum many-body problem, which is very alike to the many-body problem encountered in condensed matter physics, with some exceptions and some important differences. Well, first of all, this is the nuclear Hamiltonian, the quantum mechanical object that is basically the foundation blocks of quantum mechanics. It contains a kinetic energy term, then a two-body potential, but because nucleons are not elementary particles, they are formed of quarks and gluons that are self-bound together, there is also a three-body force. It's a genuine three-body force, like if you wanted to describe the interaction between the gravitational interaction between the moon, the Earth, and the sun, there is an actual tiny three-body force because the sun deforms the Earth. So the very fact that the sun is there deforms the Earth, and that changes the interaction with the moon. And this is exactly what happens in nuclear physics in the subatomic scale, of course. And this complicates the solution of the problem. And then nucleons are quantum mechanical objects, so they have a spin. Basically, it's a quantum number, which will be 1/2 or -1/2 associated with them. So these nuclear forces, the strength of the interaction between two nucleons, depends not only on the distance between the particles, like in the Coulomb case, the electromagnetic repulsion only depends on the distance of two electrons, for example. Here, the nuclear force depends on the spin, so whether the two nucleons are spin up or spin up or spin up or spin down, this is very different, on whether the nucleons are either a proton or a neutron and a neutron, or two protons. So basically, when solving the quantum many-body problem, we need to introduce a generalized coordinate x. So we don't care only about the special coordinates, so x, y, z of each of the particles, but we also have to take into account the fact that the spin could be 1/2 or -1/2, or the fact that the nucleon can either be a proton or a neutron. And nuclear forces couples the spin and the isospin in a non-trivial way. And well, the difficult, once the Hamiltonian is determined, and this is an ongoing area of research because the Hamiltonian is not a priori known, one has to solve the quantum many-body problem, which basically boils down to diagonalizing a Hamiltonian H and find its eigenvectors and eigenvalues. The complication here is that nucleons are fermions, so the wave function must be anti-symmetric because of the Pauli principle. So two nucleons cannot be the same position with the same spin and the same isospin. And if you exchange the coordinate of two nucleons, say I and j, there is an overall minus sign. And this greatly complicates the solution of the quantum many-body problem. Now, of course, historically, the first thing that one can do is a mean field approximation, which in nuclear physics is not obvious, because if you want, the very same problem is encountered in condensed matter. And in condensed matter, if you want to solve the structure, the quantum mechanical many electron problem, you have a central potential, which is the positively charged ion inside of the atom. So the electrons naturally move in a mean field, if you want. And then the electron repulsion is a correction to this mean field. Here, instead, there is no such a central potential. Basically, the nucleon is self-bound because of the interactions between neutrons and protons. Nevertheless, it's striking that the mean field picture works remarkably well. So in that case, the two and three body forces are replaced by an average one body potential. And in that case, the quantum many-body problem can be solved exactly under this approximation. Because basically, the ground state wave function, which has to be anti-symmetric, is the tensor product of one body objects anti-symmetrized. So it's a Slater determinant of single particle orbitals. And if you have two particles and two states, basically it's state one, particle one in state one times particle two in state two minus particle one in state two times particle two in state one. So this is anti-symmetric, but of course it neglects all sorts of correlations except the Pauli principle, the statistical one. So if we wanted to deal with the oxygen-16 nucleus, we have, say, 8 protons, and we can fill all these shells and anti-symmetrize. This is a legit wave function. similar to what you would have in the electron case. It's anti-symmetric, but it completely neglects correlations. So what happens? Well, in post-Hartree-Fock methods, one wants to find the exact many-body wave function, and one way to do so is to expand on a complete basis set of Slater determinants. So one can start from the Hartree-Fock state, in which all the energy levels below a certain level, the Fermi energy, are occupied. In this case, I have 3 particles and 7 states. So the first 3 states are occupied, and then I can construct other quantum many-body states by occupying an excited state and leave a hole behind. I can also do more than that. I can promote 2 particles and leave 2 holes behind. So it is clear that the number of particle-hole combinations, or if you want, the number of Slater determinants they can construct, grows binomially with the number of particles and the number of states. So the more states I have, the more possibilities and the more ways I have to arrange these 3 particles in that given state, and the more particles I have, up to half filling, again, the more combinations I have. And this is a binomial coefficient. And in fact, already Argonne said that the state of an n quantum particle is a high-dimensional monster. It really grows exponentially with the number of particles and with the number of states. So if one wanted to solve, say, oxygen 16 in a fairly small basis, it would require diagonalizing a matrix which is 10 to the 10 by 10 to the 10, an extremely sparse matrix. And in fact, in general, the many electron, but even the many nucleon wave function for a system of many nucleons is not a legitimate scientific concept. That was a very strong sentence. But still, we would like to solve this problem. It's an open challenge. It has been an open challenge for decades. Now, what is the hope? Well, the hope is that the Hilbert space, so as I said, these many possible combinations that we have of putting A particles into n states grows exponentially. But maybe physical states occupy a small corner of this huge Hilbert space. Well, we know that physical states are usually characterized by symmetries, for example, parity, time reversal, or rotation invariance. And we also know, heuristically, that mean field does a great job in describing most of long-range or low-resolution properties of quantum mechanical systems. So the hope is that it is possible to find order in house, if you want, so to use artificial neural networks to represent quantum mechanical states of interest. And this was the way was opened by a work published on Science in 2017 by Giuseppe Gallo and Matthias Streuer. And Dominic earlier today mentioned this work. And the basic idea here is we replace we represent the quantum mechanical wave function by a complex value artificial neural network. So the neural network takes as input the coordinates in the Hilbert space. It could be the position of the particles, their spin, their isospin, and the output is a complex number of phase and an amplitude representing the quantum mechanical system of interest. And of course, the network is characterized by weights, biases, or one can use different networks. And the optimal weights and biases can be found by minimizing the variational energy of the system. So one can compute the energy expectation value for a given configuration of weights and biases, then compute the gradient, update the weights, and iterate until convergence is reached. But as I said earlier, the Hilbert space is exponentially large. So we also need to somehow reduce the computational complexity of computing the energy. And to do that, we do sample the Hilbert space. Typically, the typical choice is to use Markov chain algorithms, but other regressive neural networks can also be designed. So reducing the exponential cost from exponential to polynomial requires 2 ingredients. One is to formulate an ansatz for the wave function that scales polynomially with the number of particles and the number of states. And 2, sample the Hilbert space. And there is one caveat. This is more mathematical oriented, of course, but it's important that taking into account the geometry of quantum state is critical to really solve the quantum many-body problem with enough precision. Here we know that two quantum mechanical states are the same if the only difference is a global phase and a global number that multiplies them. So in general, in the continuum, for example, quantum mechanical state are infinite dimensional, but in 2 dimensions, you can think of them as 2 vectors. And in fact, the distance between 2 states is not the Euclidean distance between the variational parameters. It's really the angle between these 2 vectors, because the norm doesn't matter, so we can rescale these vectors as much as we want. But the only physical quantity of interest is the angle between them. So when we actually optimize, when we minimize, instead of the art neural network quantum states approaches, instead of just using out-of-the-box optimizers like Adams or RMS-Prop or variants of it, one has to take into account the fact that 2 quantum mechanical states are different if their overlap, quantum mechanical overlap is different. So the new parameters are the old one minus the learning rate times the gradient, but then we use a preconditioner which defines the metric in this quantum mechanical space, the quantum Fisher information matrix. And this is key to achieve high precision in solving the quantum mechanical problem. But as I said, we need to get an anti-symmetric ansatz. So if you exchange 2 particles, we need to get an overall minus sign. And historically, in Quantum Monte Carlo, even before neural quantum states appeared, the first attempt is always to start from a Slater Jastrow ansatz. And by that, I mean, we can take a mean field wave function and multiply this mean field wave function by this factor j, which includes correlation. Now, in our approach, this was also used in quantum chemistry by Google, Microsoft. The idea here is that this is anti-symmetric, this is symmetric, and therefore the product is anti-symmetric. And in our work, we use simple multi-layer perceptron to define the single particle orbitals. But for the Jastrow, for this permutation invariant factor, one of course could symmetrize it by hand. So you take, for example, 1, 2, 3, 2, 3, 1, you sum over all possible permutations, but this scales factorially with the number of particles. So fortunately, there is a theorem saying that any permutation invariant function can be sum decomposed. So what we actually do, we define 2 neural networks, phi and rho. Then we do, at the very beginning, we do just that. And basically, you apply the same network phi to all coordinates, single particle coordinates, and then you pull over them. So we destroy the ordering, and then you apply a network rho. So here, the idea is that because of the sum operator, this functional is permutation invariant, and it's also universal. So it satisfies the universal approximation theorem. And what we did back in 2021, we solved the deuteron, the most simple nuclear systems consisting of a proton and a neutron. And what we did, we basically minimized the energy for 2 different nuclear potentials. These are just regulators, but we don't have to worry too much about them. But the idea is that after a few, just 100 optimization steps, you are basically converging to the value that we can obtain with exact diagonalization, because this is a mode system and you can solve it in a numerically exact way. So this was promising. But then this ansatz is powerful, but it's not universal. It is not true that any anti-symmetric wave function can be represented as a product of a symmetric one times an anti-symmetric zeta determinant. So what we did, we said, okay, we can enhance the expressivity of these ansatz by including hidden degrees of freedom. So a standard Hartree-Fock state is basically this upper left corner in which we have 4 states, 4 particles, and that's purely uncorrelated. What was shown in this paper was that one could add fictitious particles, y, and fictitious states, chi, k1 and k2, and then couple them in this way. So compute this extended zeta determinant, so that if y are permutation invariant function of x, if I exchange, say, x1 and x2, these 2 columns swap. So I got, and this one remain unchanged because y is permutation invariant function of x. So I get a minus sign overall. This function is anti-symmetric. And on the lattice, it can be proven that this is a universal approximator for anti-symmetric functions. In the continuum, there is no such a proof, to the best of my knowledge. So we just tried it because we are working in the continuum and compared with state-of-the-art methods. And this is a pictorial representation of what's happening. So in the real world, nucleons are very, very much correlated. So in fact, they are very entangled. You cannot write the wave function of any body system as a product of one-body wave functions. What one can do, one can introduce additional fictitious or hidden degrees of freedom, this blue, spheres here. And now the interactions among these five nucleons as a whole is much weaker in a sense. So they mediate the strong interactions among these, the real particles, so that in these five bodies, the quantum mechanical wave function of this five body system is actually a Slater determinant, a single Slater determinant. That's a trick of reshuffling correlations, including fictitious degrees of freedom. And so, armed with this wave function, we computed the ground state energy of oxygen 16, which is already very demanding. It's basically the limit for state-of-the-art conventional quantum Monte Carlo methods, increasing the number of hidden nucleons. And we get these blue points. So we do better than state-of-the-art diffusion Monte Carlo, in which basically we have to spend a lot of computing time to control the Fermi problem. This is why there is this orange band. So this is very, very promising because this costed us a fraction of computing time. It's like hundreds of hours on a GPU compared to millions of core hours on a CPU. And not only that, we can also compute what is the probability of finding a nucleon from a given distance from the center of the nucleus, the density profile of the nucleus. And in our case, we compare, again, state-of-the-art quantum Monte Carlo in orange with our neural network ansatz in the blue, and they perfectly agree. But the point I want to stress is that here in the blue, there is no a priori information on the shell. So the single particle orbitals are randomly initialized. There is no shell structure whatsoever. There is no spherical harmonics, nothing. Everything is learned by minimizing the energy. And yet we see the p orbitals with a peak at a given distance from the center, which is typical of the oxygen nucleus. So basically, there is self-emerging shell structure. In a sense, the network can really understand quantum mechanics in a sense, just because of the anti-symmetry. Then what we did more recently, we pushed our calculations up to neon 20, so from oxygen 16 up to neon 20 using two different potentials, and I'm comparing here the computed ground state energies with two different versions of the three-body force by orange and green, compared with the experimental value, and we can reproduce the trend very well, solving the Schrödinger equation with unparalleled precision. We don't do that well with radii. This is a symptom of the fact that this Hamiltonian is not the most accurate one. So we need to improve not in the way we solve the Schrödinger equation, but in the input Hamiltonian. And this is another key of this approach. So if we are able to solve the Schrödinger equation with high accuracy, we can actually tell, we can elucidate what is the nature of nuclear forces. There is no unique parameterization of a force between a proton and a neutron. Okay, it is not possible to solve QCD from first principle. And so they are parameterized in terms of energy constants that need to be fitted to data. And this is a way to do that, to access really what is that binds nuclear. Then I wanted, in addition to binding energy in radii, we can compute the electromagnetic properties of nuclei, see the magnetic moments. But now, what happens is that the network is degenerate. So the ground state is degenerate. For the Hamiltonian commutes with the total angular momentum, but if the angular momentum, say, is 1, then its projections plus 1, 0, and minus 1 will give exactly the same energy. So by just minimizing the energy, we end up in a linear combination of eigenstates of the total angular momentum LZ. And it could be oriented in a random directions. But to measure the magnetic moment, we need the angular momentum to be aligned, say, to the z-axis. How can we do that? I mean, how can we break the degeneracy? Well, we can do like in experiments. We can add a small external magnetic field to the Hamiltonian, so that if the orbital angular momentum and the magnetic field are anti-parallel, then the energy is mean. So basically, this favors, we are favoring an orientation of the angular momentum, which is along the positive z-axis. So first, we just train the network, minimize the energy without external electromagnetic field, and we turn on the magnetic field, and we expect something like that to happen. So the nucleus will rotate until the orbital angular momentum is anti-parallel to the magnetic field. And this is actually what happens. So here, this is lithium 6. What happens is that this is after just the regular minimization of the energy. The projection of the angular momentum is a kind of random. Then we turn on the magnetic field. What happens is that the energy remains the same, but the angular momentum changes. And then we turn off the external field, and the nucleus relaxes to the position that we want. So we break the degeneracy, and then we let it stays there. And then here we can actually measure the angular momentum. And this is what happens for the magnetic moment. And this is actually what happens with the magnetic moment, and this value is in excellent agreement with the experiment. So we can actually, the cool thing is that not only we have a self-emerging wave function, but we can actually manipulate it by adding, for example, an external magnetic field. All right, let me do a brief condensed matter detour, because these two fields are strongly connected, because we're interested in low-density matter found in the interior of neutron stars, basically superfluid neutrons. In this case, forget about the isospin, we only have one species, neutrons. And the degrees of freedom are this separation distance and the spin. It happens that one can recreate basically this condition in the lab by tuning the interaction between atoms in this case. So we're no longer talking about nuclei, but really atoms. These are atoms. And these atoms have a spin. And one can tune the interaction between opposite spin particles so that one can actually have a crossover between the BCS and the BC phase, the bosonic and condensated superfluid phase, going through the unitary. So these are pair of opposite spin particles. If the interaction is not that strong, there is a superfluid. In the unitary limit, the interaction is extremely non-perturbative. And then here instead, the interaction is so strong that opposite spin atoms form a molecule. And describing this phase transition is extremely hard. Just to model it, we can just write a two-body, simple Hamiltonian with a kinetic term, which is similar to what we find in nuclear physics, and a two-body potential. And the two-body potential is only active between opposite spin particles. So same spin, no interaction, opposite spin attraction. And this is how the potential looks like for different ranges. And this is the analytic expression if you're interested in. Then again, we need to solve the quantum many-body problem. But what we came up with is a generalization of a function that is used to describe strongly paired system, where pairing, quantum mechanical pairing has a strong effect, which is the Pfaffian. This replaces the Slater determinant in the following way. So instead of working with single particle wave functions that we have to learn, remember in the Slater determinant case, we came up with the idea of using this Pfaffian, which is basically, it starts with by constructing a pairing orbital, which is an antisymmetric function of two particles, and then arrange the particles that we have in this this antisymmetric partition in a possible way. So basically, if we have just four particles, we can arrange particle 1, 2 in the first 5, 5, 1, 2 times 5, 3, 4, and then we have all possible antisymmetric arrangements. So 1, 3, 2, 4, 1, 4, 2, 3. And these ansatz already encode by default pairing correlations. And the network now, instead of having, the crucial point is that now instead of having one neuron network for each orbital, we have one neuron network. We only need one orbital. So we have one neuron network for the whole system. So that means that the number of parameters does not grow with the number of particles. It is basically fixed. This is a critical advantage, and we have way fewer parameters than before. And following this work by Luo, back in 2019, we actually announced the expressivity of the network by transforming the original coordinates into new ones. So you can, again, think of starting from the physical coordinates of these cold atoms, X, Y, Z, and the spin, and map them into a new set of coordinates which depend on all the others. So these coordinates already encode correlations, and they might live in a much bigger space. So here the idea is that, again, we have three particles which are very, very correlated. Then we map this system into another one, which could be higher dimensional, but where correlations are basically smaller, and then there is basically only pairing correlations. Well, let's skip the details. We use a message passing neural network to do that. But what we found is that we can compare with the state-of-the-art diffusion Monte Carlo calculations in blue, and we do consistently better as a function of the number of particles. And the idea here is that we need to reach the thermodynamics limit, which is already 66 particles is considered enough. And the ratio with the non-interacting case, the energy that if we compute the ratio with the non-interacting case, we obtain the converged parameter, which is in much closer agreement with the experiments than diffusion Monte Carlo. And this is a kind of technical. I want to go back to neutron stars and to nuclear physics. As I said, we developed this architecture as a warm-up because what we are really interested in is what happens in the crust of neutron stars. And this is textbook. So you can think about problems of a neutron star as a giant nucleus in a sense, but it's more complicated than that. So in the crust, we basically have regular atoms. The density is not so high. But then as the density increases, the electrons are basically stripped away. And what happens is that one is left with the neutron-rich nuclei surrounded in a lattice of electrons. And then again, as the density increases, these electrons become more and more neutron-rich, and because of the Coulomb repulsion between protons and the strong attraction between neutrons and protons, there is like very, very strange shapes. Like these are called like pasta shapes, like fusilli or spaghetti, depending on the. It's really a frustrated system. And then in the end, this nuclei dissolve, and everything is like a fluid. Protons and neutrons form a fluid. And this is impossible, basically, to describe microscopically. So starting from the individual interactions between protons and neutrons, most means. So what we did, we actually used this Pfaffian ansatz, we generalized it to incorporate spin and isospin degrees of freedom, because now we're back to nuclear physics. And in the zero density, if we simulate, say, 14 protons and 14 neutrons in a box with periodic boundary conditions, what happens is that in the zero density limit, if there is no clustering, the energy of the system is zero, because these particles are infinitely far away. The box is huge, and you have 28 particles sitting infinitely far away, the energy is zero. If instead there is clustering, and in fact in the limit that silicon-28 is formed, so actually the 14 protons and the 14 neutrons are always together, the energy is the one of silicon-28. Okay, you have many silicon-28 very far away, but the energy is the one of silicon-28. And this is actually what happens. So conventional quantum Monte Carlo results this is as a function of the density. This is basically the transition between the core and the crust of the star, and here I'm decreasing the density. Conventional quantum Monte Carlo approaches, because of the Fermi-Einstein problem, they predict basically no clustering and a liquid at all phases. So basically these particles are very, very far away from each other, and the energy of the system is zero. Our neural network quantum state approach instead predicts the blue curve, which converges to the energy of silicon-28, which we can compute independently. So this is the first microscopic calculation of this kind of matter. Okay? Of course, this is still not realistic, right? Because we're only simulating 28 particles with periodic box boundary conditions. The thermodynamic limit is very far away, but still, this is an indication that we can actually see the self-emergence of clustering. This is really quantum many-body matter self-organizing itself. There is no information on clustering whatsoever in our answers. It just self-emerges, emerges from minimizing the energy. We can compute this as an important impact because in the proton fraction. So one can ask how many protons are there, how many neutrons are there at a given density. Well, if there is clustering, so if you just have neutrons, it's a liquid, a superfluid liquid. There is no clustering whatsoever. But if there are protons in there, forming clustering lowers the energy of the system. So it becomes favorable to have more protons than just neutrons. And this is exactly what happens. So in the standard absurdity, quantum Monte Carlo calculations predict a very small proton fraction because it's not that convenient to form protons. But now that we do have clustering in it, self-emerging clustering, the blue, we obtain the blue points, and there is actually more protons than in the crust than the state-of-the-art diffusion Monte Carlo calculations predict. And our results are consistent with the energy density functional predictions that are based on terrestrial experiments for atomic nuclei. And this is basically a cartoon of what's going on. Here I'm printing the coordinates of the protons and of the neutrons. These are 14 protons and 14 neutrons at 0.01 Fermi to the -1, so low density regime in the liquid phase. Here there is no interaction. And basically you can see that they are uniformly distributed. There is no clustering whatsoever, I mean, at least by eye. But then we can turn on the interaction, minimize the energy, and print again the coordinates. And you can see there is really clusters of silicon-28 forming. And we use the same ansatz both for the liquid phase and for the clustered phase. And we can repeat the same experiments putting only 4 protons, liquid phase, and in the clustered phase, we see the formation of, say, beryllium 8. Okay, and this is all self-emerging from the minimization of the energy. This cannot be seen using any other quantum many-body methods. So let me do my conclusions now. So what we can now do that couldn't be done previously within quantum Monte Carlo methods is actually to explore the entire nuclear chart. And in particular, these new isotopes that are expected to be measured at F3 at MSU. And this will help us elucidating the nature of nuclear forces, because we can test our Hamiltonian on a much wider set of nuclei than currently possible. And importantly, this approach can cover both can model very well both long range and short range dynamics. So like long range properties like binding energies and radii, but also very short range properties that are measured by doing semi-exclusive electron scattering experiment on the nucleus. So for example, we can resolve the configurations in which two protons, a proton and a neutron basically overlap, and there are genuine quantum chromodynamics effect at play. So one thing we are now working on is real-time dynamics. So neural network quantum states open the way to do real-time dynamics, and they are the only method that can do that. And we're interested in, of course, fission and fusion. And these two processes can only now be modeled, except for very light systems, only modeled using time-dependent artifacts on electron correlations. And we can do that for the first time. And here with people at MIT, we're encoding symmetries. Encoding symmetries into the ansatz is not that easy when we deal with fermions, but it can be done. And we can encode, for example, rotation invariant, but more importantly, we want to encode S2 symmetry. Yeah, and that's it. Thank you very much. Okay.
We always have time for a few questions.
Very interesting. So when you're adding these fake particles to account for correlations, like for called baryons in other cases, you see this asymptotic improvement in the number of baryons that you add. Have you been able to find any sort of pattern to this connected to the number of nucleons or some kind of symmetry, how many you need?
Yes, that's an excellent question. So in the original paper on the lattice, it said that one extra particle is enough to describe any anti-symmetric wave function. We tried different nuclei and we always found convergence when we added as many additional particles as real ones. So we were somehow, I was trying to prove that that was actually a requirement. But then we came up with this message passing neural network, and then with one, we managed to converge. So it's not clear on the continuum what the situation is. Now I'm more inclined to think that one is enough, but the proof that's on the lattice cannot be, it's not valid in the continuum because it requires constructing lookup tables. And if you have continuous degrees of freedom, you cannot do that. You can only do that approximately. Yeah, but we don't know.
Your question?
Thank you for the really nice talk. I've seen also other work trained on neural nets, trained on nuclear physics data. And I've also seen that the nuclear shell model is also emerging without actually incorporating information. But of course, this was, for example, others were just taking this as a regression problem, not solving the quantum many-body problem. So I'm just wondering, do you think that are we looking for neural nets to give us, for example, new model for nuclear physics, or are we looking for neural nets to help us, for example, predict the properties for new isotopes, etc.? Yeah.
Yeah. So here, basically, the building blocks, the only input is the nuclear Hamiltonian, which is determined on nucleon scattering data. So it doesn't end on the binding energy of, say, 3 and 4 body systems. Everything else is prediction. In other models that do not, in other neural network approaches that do not solve the quantum many-body problem, say, one can use neural networks to predict the masses of given nucleus, starting from the number of protons and the number of neutrons, training on existing masses. In that case, in our case, we're really opening the box. So we are solving the quantum many-body problem. We're starting from first principles. So we can predict not only binding energies and radii, but many other observables that require knowledge of the wave function. For example, we can compute magnetic moments or weather decay. For example, one interesting question to answer is why carbon-14 is so long-lived that allows us to do carbon dating. And you cannot answer this kind of question without opening the box. So you need to open the box, look at what happens at the quantum mechanical level, and then try to figure out why it lives so long. Okay, so it gives a lot more information than just global mass fits, for example.
Thanks for that talk. As far as I remember, in DeepMind's recent AlphaFold version, they basically scrapped implementing symmetries in their network explicitly. And it seems that in your kind of problems, this is really crucial to incorporate these symmetries in these networks. Why do you think the situation is different in this case?
It is not in this, it accelerates the training. So the only symmetries that we now encode is parity and time reversal. And these are symmetries that we know are there because of the Hamiltonian. The neighbor Hamiltonian conserves parity and time reversal. And we try not including them and including them, and what happens is that we converge to the same energy, but it's much faster if we encode them directly. So it's a matter of saving computing time. Now, I have mixed feelings about symmetries because on the one hand, they accelerate convergence, that's for sure. But then if you impose them, you cannot use them to test your result. So suppose that we know from nature, from experiments, that the ground state of oxygen-16 is angular momentum 0. Now, if we impose it, we know that it's 0 no matter our optimization. If we don't impose it, we minimize the energy, and then after the fact we test, we compute the angular momentum and we check it's 0, then we are more confident that we converge to the actual ground state. So I don't know if this answers your question, but it is important, I think, to include symmetries to speed up the training, but it's always important, it's always a good thing to check that they are respected even if they're not imposed, at least in a few test cases.
Thank you very much. It's really fascinating and nice progress. Can you comment a little bit about time dependencies? So people do mini-field like time-dependent Hartree Fock or DFT, they do fission, fusion. You had a sentence in your last slide. Can you talk about reactions and time dependence?
Yes, yes, absolutely. So if you, sorry. Time dependent allows you to go beyond the linear response regime. So if one, and this is the case of fusion and fission. So you really, and scattering. So if you really want to do nuclear scattering, fusion and fission from first principle, you need to do time dependent variational Monte Carlo in this case. For electron scattering, at least for the inclusive one doesn't need to go that far. There are other ways of computing the inclusive electron nuclear scattering cross sections that don't require doing the full real-time evolution. But the moment you want to go more exclusive, then you need to do that. And this is what we're actually doing now. We are computing in real time the density response of a nucleus. So basically, there's an electron coming, transferring momentum to one of the nucleons. And we can evolve in real time the wave function of the nucleus after you interacted with the electron. So basically, we can see the nucleon going out. And we can quantum mechanical way, so retaining more quantum mechanical correlations, at least for some time. But then there is noise and some other technical issues that we're dealing with. But this is, I think, a new avenue of research for us.
So it's going in the direction you can do the full transport,
Yes.
the nucleus, final state, also consistently?
Yes.
Amazing. Thank you.
I think we have time for one final question. Anybody wants to take me up on that? Okay. Well, thank you, Alessandro, again.